formal definition. So in the formal definition, it means we're going to use proper mathematics to define everything about the reinforcement learning. Because mathematics is the language of science, it makes us precise. It's very powerful. All our science and technologies come from mathematics, right? In computer science, it's the same. We use mathematics to make a theory, and then we derive many useful properties, including our algorithm, reinforcement learning algorithm, and then we just program after we have the mathematical formula. But before we go to that, we have to define things properly first, okay? So as I mentioned to you, in reinforcement learning, we have two models. So the first is environment, and the other is agent. And we're gonna define the two of them properly in mathematical notation. I told you before that we assume that environment already exists. We don't have to program it by ourselves. Still, we have to understand environment properly in mathematical details, because still our agent gonna get input from the environment, right? And we have to understand this input clearly so that we're gonna program properly, process the right input, understand all the meaning, and make the efficient agent. Okay, on the environment side, it called Markov decision process. So Markov decision process is rather as maybe a big name to you if you are not familiar with the probability. But anyway, it's not quite important to understand the meaning of this one. But you're gonna see this MDP or Markov decision process everywhere. You go study reinforcement learning in any lectures, in any book, you're gonna see this MDP. So at least you have to understand when you see MDP, it means environment. It's the proper mathematical notations of your environment. Okay, let's start. This is the same reinforcement learning diagram that we just already talked in the previous slide. We're gonna make it more formal. Okay, now you can see we change all the English words to proper, mathematical notation. Don't get scared. Let's start from the easiest one. Okay. Let's start from the action, the agent action. Okay. So actually, AT is simple. It means action of the agent at time step t. Okay. So t here is the time step, and A from action. It makes sense. A here, you notice that this calligraphy A here has a different font from A here. They are both capital, but this one is action agent at time t, and this one is like a calligraphy. It's like a handwritten character. It usually denotes set. Okay, so this is a set notation. It means that the action at the time t belong to all possible actions set. Okay, so this calligraphy set A is denote the all possible action. Also the same for this set S, calligraphy S. It also denotes the set of all possible observational state that the environment can send it to you. But the real one that you observe at the time step t is this normal capital ST. Okay. So ST is the observation that you're gonna get at time step t, and the reward here we just denote it by RT. It makes sense again, right? Because reward is R. Okay, and to say that the reward it just belong to real number, it also makes sense because we said it before that the reward can be like a 10,000 or minus 10,000 or 0. They are a real number. So this is a very simple thing. So you see, we can map one to one. So the agent send action A at time step t. This action have to be well defined. This had to be in this possible set calligraphy A. You see, it's the same thing as is this in English text. This is also the same thing. Environment send the state after getting the action or the state at the time step t, as well as the reward at time step t. Okay, so they are the same thing. Just use the mathematic notations. Okay, this one, the environment model, is a conditional probability. It looks a little bit more complicated compared to these guys, but actually nothing complicated here. The trick is you have to read it from back to front. Okay, so here it's a conditional probability if the agent is in state st and agent just perform the action at. Okay, so the environment gonna generate the next state st plus 1, okay, the state of the next time step t plus 1, as well as the reward at the next time step t plus 1, based on the current state and the action, right? This makes sense because we know that the new state and the new reward depend on the current state and agent action. So the probability PR here denote probability. This is you can interpret like all possible state and reward that can happen, condition or given by the current state is st and at. Okay, so this notation is just like a environment information. It's gonna encode all possible state of st and rt plus 1 in the next time step given the current information. We're gonna see more concrete example in the next slide. But anyway, in the Mario example, st, as I mentioned, it can be just a screen, okay? It's just a single picture that the agent can process. So this is an example of the observation st, and reward at the time step t can be just 0 because nothing happened. Okay, so 0 and this picture gonna send to the agent, and agent send the action. Maybe Mario gonna move to the right, and then the environment gonna read this st, the current state, and the action that the agent do, and gonna use this information to generate the next state t plus 1 at the time step t plus 1 and the reward at the next time step, and send it back to the agent. So if the Mario is moved to the right, the screen gonna move to the right too. And all of this together, you see the conditional probability and the possible states and possible action, these three things together, you can see that these three things together explain all of the environment. That's why you can define the environment formally using these three objects. And the set of these three objects, we just call it MDP, or Markov decision process. Okay, so the Markov decision process is the set of these three objects. If you understand these three objects, you understand clearly the environment. By the way, what is the set of all possible state here? If the state in the Mario game is the picture, the set of all possible state actually is like a all possible picture, right? All possible pixel that can happen. You can vary anything and you can send to the agent. But for now, let's just talk a little bit more about the environment, right? So here I said that the environment defined properly as a set of possible state calligraphy S and A, and also conditional probability. And if you go to use the existing environment, I mentioned that in our course we use the existing environment, right? So one of the popular library that we're going to use is Gymnasium, and is the example of the environment game is Frozen Lake. Okay, it's a simple game, and in each game, not just this game, in every game, you can see that in the document of Gymnasium, it's going to explain to you about the action space and the observation space. Okay, so it's the same. That's why you have to understand MDP, because even in your even if you want to program it, you have to use the same knowledge. There is action space, observation space, and also the conditional probability of how this observation just transition from previous state to the next state. Okay, and actually this frozen lake is an example of the very simple game generally called grid world. It's the like a hello world on reinforcement learning, and we're gonna consider this guy, the robot guy. Actually, they are the same game. So this game is really easy. You have all the information of the map. You know that this map gonna get you win +1, and this map gonna get you lose -1. Be mindful, in some game you may not know this, but in this game we assume that we know this. Okay, we know that you're gonna get +1 here, -1 here, and also this game too. You're gonna get +1 here, -1 here. If you go to this -1, you fall down and you die. But if you go to +1, you win. When you win or you die, the game just restart again. The game just restart again, and you continue to play again and win again or lose again, and hopefully your agent can learn how to win consistently. In this simple game, it's very easy, right? If you are here, you just go move up, right, and you win. But the agent doesn't know this at first because it has zero knowledge of the world. But anyway, in the next lecture, the next 2 weeks, we're gonna learn how to program the agent. But at the moment, let's just assume that if you are human, you want to play this game, what you gonna do? Okay. So the state of the game. I mean the this tile, the +1 and -1, they have special names. They are called terminal states because when you are in this state, okay, you're gonna win or lose and the game restart, right? You're gonna start a new game. So whenever you arrive at the terminal state, you just go back to start again. So it special states of the game, and you play again and again. The game that you play again and again and have terminal states like this is called episodic game, and your model is also called that you learn in like a episodic learning. Okay, and when you start again, it's called that you are going to you play a new episode. So this is a standard terminology. When you read reinforcement learning book, you're gonna see this word. I mean, episodic learning, a new episode. So it just means that you restart a new game and you learn again and again. Okay, so now with this simple example, we're gonna use it to illustrate the MDP with the conditional probability, state space, and action space, just to make example and make sure that you clearly understand everything. In this grid world, we use a simple example that the map is fixed, so that if the agent win or lose and the game is restart, the map is the same every time. You play the same game every time. It's a boring game, but it's easy one, right? And we're gonna consider two cases, easy deterministic cases and a little bit more difficult noisy cases. But anyway, we're gonna just consider deterministic case first. Okay, so in this simple game, the map is fixed and everything is deterministic. Okay, let's see what is the MDP. The action is the most obvious one, right? In this game, the agent can go left, right, up, and down. Okay, so the action space is the set of 4 objects, left, right, up, and down. It means that the agent can send this 4 action to the environment, and the environment understand. If you send any action that is not in this action set, the environment will not understand you. Okay, so make sure that you understand action space, and whenever you play a game, you send only the action that is belong to the action space only. And the state space here, what is the state space? Because the map is the same every time. Okay, what is different between each state? What is different between you send the action that you move up, you move left, you move right? The map is the same. So the only thing that change is the position, right? So here, the position of the agent itself is the state of the game. Okay, it's not like a Mario game when you move to the right, the map is changed and you have the totally new state, the new picture. But here, everything, the map is the same. Only the agent is moved to the different position. So you can simplify the state space to be the position of the agent. You can make all the picture, everything as a state too, just like a Mario game, but it's not efficient because you can simply represent the states as a position of the agent and you have the same information. Okay, so here the state space, the simplest one, it can be the position of the agent because there are 12 positions. You can label it as 0, 1, 2 until 11. Okay, it is arbitrary. It can be 1, 2, 3, 4 and to 12, anything. Okay, so is it clear? I mean, if the environment send you now you are on stage 2, you understand, right? That agent is here. If the agent say now you are on stage 9, it means that agent is here, the map is the same, so you understand everything. That's why the state is complete. This definition makes sense. Okay, when you understand the state, if you know the state, you know everything about the game. Okay, now you understand action space and state space of this simple game. Be mindful that in more complex game, the state space can be more complicated. For example, if the map change every time, the state space will not just be a position anymore because the map also change. But we're gonna look at this case in the next slide. Okay, but for now, just focus on this easy case. So now we understand state space, action space. What is the conditional probability? Okay, it is more details, but in this case it's still simple. So the conditional probability is a probability. You know that probability had to sum to 1, right? Had to sum to 1, or possibility had to sum to 1. But it's also, it depends on each input. Okay, so for each input, for each state and action of the agent, probability of or possibility had to sum to 1. Okay, let's see the example. Here, suppose the agent is here on state 2 okay, and the agent decide to go up u. So we can write the conditional probability in this notation. In the deterministic case, we know exactly where will the agent go, right? So here, the agent is here on the second state. When it go up, it will arrive at the state 6 for sure because it's deterministic. It's just the rule of the game for this game. For the noisy game, it may not be the case. But for this deterministic case, the agent always go up correctly. So you know that we write this information like this. So if the agent is on state 2 and go up, okay, given this is called given this information, the probability that agent gonna go to state 6 in the next time step with 0 reward, right? You know, because the state 6 there is no reward here. This probability is equal to 1, and probability of everything else given the same condition is 0. For example, probability of agent gonna stay on state 2 with 0 reward equal to 0, right? Because we know that the probability had to sum to 1 of the same condition had to sum to 1 because this possibility, this state 6 with 0 reward already have probability of 1. It means 100%, okay, 100%. So all of possibility or other possibility have 0 probability. It should be clear. Let's look at the other example. If agents stay at state 2, the same thing, and move to left, decide to move to the left, so agent gonna move to state 1, right, in the next time step. So probability that the next time step agent gonna be in state 1 and get 0 reward here equal to 100%. It's the same if it go to the right. The next time step it will go to the state 3, 100%. And if it go down, because there is no place going down, it will stay at the same place. So it will result in state 2, also 100%. So yeah, you have this kind of information in the environment. Okay, if you have to program the environment, you have to program all this information, and then the environment gonna use the information to calculate the next state, right? So if the agent is in state 2 and move up, the environment know that okay, the next state have to be 6. So it's easy. So overall, the environment have like a big table of 12 state clause for action of all possibility of this probability information. Okay, I hope it's clear. Next, let's consider more difficult game, the noisy game. In this noisy game, it's not deterministic anymore. It means that when your agent decide to go to left, for example, it has 20% that your agent gonna slip to the right instead, okay, to the opposite direction. So 80% of the time, your agent going to go to the left according to your action, but another 20% it go to the right. So imagine that you place the left 10 times, 8 times it's gonna go left for real, but 2 times it's gonna go to the right. So actually both you and agent may get confused, right? Because this is the rule of the game. It doesn't make sense, but it's just the game that you play and you want to win. Make sense or not? Anyway, in this silly game, noisy grid world game, you can write conditional probability in more details, similar to the previous deterministic case, but a little bit more details. So the same example, if the agent is on state 2 and you want to go up here, you know that 80% of the time you're gonna go up for real. So you write like this. So probability that given that you on state 2 and want to go up, you're gonna go to state 6 with 0 reward. This probability is equal to 80%. Okay, and the probability that with the same condition, but you're gonna result of going down, but because there is no down here, right? So you stay in the same state. So you're gonna stay in the same state too with 0 rewards. This probability of this state equal to 20%, and there are only 2 possibility in this game, and everything else has 0%. Okay, it doesn't happen. For example, that the probability that you're gonna go to this reward state is 0%. I mean, it cannot happen in this game, but in the other game it can be happen. But in this game, the rule is clear using this conditional probability. Another example is very similar. Okay, so if you on the same position, but you want to go to the left, okay, you action to the left, 80% of the time you're gonna result in the state 1, which is on your left for real, but 20% of the time here you're gonna be result you on state 3 instead, because it's slippery, it's noisy, just the rule of the game. Okay, you still have the big table of 12 state clause for action of this probability information. It's just a little bit more details than deterministic case, but it's still the same. Okay, so if you have to write this environment in your program, for example Python, you have numpy array of all the possibility of 12 state and 4 action, and you have to fill the information. Okay, so this is the easy case that we consider before when the case that the map is fixed, right? But how about the more difficult version, when every time that you win or you lose and you're gonna get to and you're gonna get start, the map change every time. Okay, the map change every time. You have different stone here somewhere else, or maybe not exist at all. The winning position and loss information maybe somewhere else randomly. Yeah, so it's arbitrary every time. I mean, this game is more realistic, right? You train the agent to play on a arbitrary map. It should better than training the agent on one single map, like last example. Because in the last example, your agent can win on one map, but when you change the map, the agent doesn't know what to do. It will not make the optimal action. Okay, so if you can win this arbitrary map game, your agent is considered more intelligent. But anyway, in this case, what is the MDP? Especially what is the action space and state space? The action space is actually the same, right? Because no matter what the map is, you always have 4 action: left, right, up, and down. Okay, but what about the state space? Now the position is not enough anymore. When you consider the information is enough or not, you have to understand the state of the game given the state. So if the map is arbitrary, and you know that the agent is in this position, you still don't understand the current state of the game, right? Because you don't know the map. The stone can be next to you, and the winning position can be here, but you don't know. So for each type of the game, even though the game is similar, you have to be conscious about the MDP. Okay, so it's the key. So maybe you write the agent to play on similar games, but it can happen that they have totally different state space or action space. You have to be really conscious about the MDP of your environment. So this is the key. Yeah. So the solution of the answer of the question, the previous question, that if you play this arbitrary 4x3 grid world game, what is the state space? The state space have to be two things. Okay, so the state space have to be our possible map information together with the position. In the fixed map case, you have only position information, but in the arbitrary map, the environment has to send the position as well as the current map to you. Okay, so in addition to the current position 0 to 11, just like last time, the environment also have to send this map information to you, and the map information can represent as simply the numpy array which shape 4 cos 3 cos 4. I mean 4 cos 3 because we live in this 4 cos 3 grid world, right? And this 4 represent the 4 possibility of the tiles. So we have normal tile, stone tile, +1 tile, and -1 tile. Okay, the agent doesn't have to know the knowledge of the start initial state. The game just reset the agent anywhere, but the agent doesn't have to understand this starting condition. So that's why only 4 possible states is enough for the agent. Okay. Actually, this is one possible example of the state space, this numpy array together with the position. But actually, you can also send all this picture to the agent, right? All this picture can be state observation too. But yeah, just like my real game, everything can be every game can be represented as the picture, but it's not efficient because to represent everything as a picture, you have to define a lot of pixel, color, everything, and yeah, you use a lot of memory. By simply define it as numpy array of 4 cos 3 cos 4, you save a lot of memory, and your agent can process this information much easier. Okay. In your homework, I'm gonna send you the homework properly, maybe before lecture 2. You have to try to define and explain the state space and action space of these two games. Yeah, I will write a formal definition of this problem.